So thanks everybody. So yeah, today, as mentioned, I'm going to talk about kind of a theoretical survey of equilibrium mass laws for different types of materials, building on a lot of work that's already been done, and in most cases agreeing with that earlier work with my co-author, Ed Young. I just want to, first of all, acknowledge that there's going to be some data shown here that comes from other people who aren't co-authors, like Isaku Cole at UCLA, and some of the early part of this work was done in collaboration with an undergraduate, Andrew Magracia. He was a UCLA student several years ago. Oh, excuse me. There we go. So I'm just gonna give a very simplified overview of sort of what we're talking about when we talk about equilibrium processes and the mass laws for 017, 016, and 018 relative to each other. And I'm going to start with perhaps the simplest relevant example, which would be a carbon monoxide molecule. And so, how do we actually separate isotopes at equilibrium? Well, this is the basic idea, that at least the dominant effect that I'm going to be talking about today that seems to be important for oxygen. So if we have a carbon monoxide molecule, there's a bond there. If you think about the energy associated with that bond as a function of the shape of the molecule or its bond length, there's going to be some energy trajectory, and there's going to be a minimum energy at the equilibrium bond length, right? So there's going to be a minimum in that potential at some equilibrium bond length, which we could just call R0. But we live in a quantum mechanical universe, and that's what's really important for equilibrium isotope effects, such that even at the lowest possible state of the molecule, because vibrations of that molecule are quantized, there's always going to be a half quantum of vibrational energy present. So 1/2 times Planck's constant times the vibrational frequency, 1/2 h nu, even at the lowest possible quantum state. And in addition, of course, there are going to be excited states, but this concept of a minimum possible energy, the 0-point energy, turns out to be the main driver of equilibrium isotope effects, and ultimately variations in 017 at equilibrium. Okay. So let's put some numbers next to that. So here we're showing some vibrating carbon monoxide again. And of course, there are 3 different oxygen isotope versions of the carbon monoxide molecule. There's C12O16, C12O17, and C12O18. And I've just shown here the vibrational frequencies of each of those isotopic forms in the harmonic approximation. And what you can see is that as you substitute progressively more massive oxygen isotopes, you get slightly lower vibrational frequencies, exactly as you would expect. The sort of intrinsic potential is the same for all of these, but the inertia of the molecule with respect to vibration is increasing, and so the vibrational frequency decreases a little bit. But if you convert those frequencies to 0-point energies, that lowest attainable energy with a half quantum, you see that there actually is a difference in the energy between these molecules of about 300 joules per mole or something like that, such that the isotopically heaviest form of CO is about 300 joules per mole more stable than the lighter isotopic form. It's harder to break that bond because the vibrational energy at the ground state is lower. So we can go a little bit farther and actually use that observation to estimate an equilibrium isotope fractionation associated with carbon dioxide. And here I'm going to do it in perhaps not very geochemically useful, but theoretically convenient exchange equation, where we have a carbon monoxide molecule that's exchanging oxygen isotopes with atomic oxygen. So a pool of oxygen atoms that are not bonded to anything else. They're just floating around as ideal gases. And in this case, because atomic oxygen doesn't vibrate, it doesn't have anything it's bonded to, the only energy term that turns out to be relevant, or at least the dominant energy term that turns out to be relevant in deciding how this equilibrium behaves, is that 0-point energy of vibration in carbon monoxide. And so in this particular case, where in the reactant side, the O18 is in the carbon monoxide molecule, that's the more stable side of the reaction because it has the lower 0-point energy, and equilibrium favors the lower energy part of the reaction. And so in this case, you would expect the reaction to lean to the right, to favor the right. The equilibrium constant would be greater than 1. because there's a free energy driving it that way. And so if we just, put in the equation many of us sort of have nightmares about from our high school chemistry class final preparation, it works out to something like an equilibrium constant of 1.13 at 25 degrees Celsius. The general rule here is that you get about 1 per mil for every 2.5 joules per mole at room temperature. And so that corresponds to about 13% more O18 going into carbon monoxide in equilibrium with atomic oxygen at 25 degrees Celsius. And of course, if we did the same exercise with O17, we'd get a separation of about 7%. That's equivalent to 130 per mil or 70 per mil if you do it in per mil notation. Now, this is just a sort of to give you hopefully a little bit of a intuitive idea of what's going on when we do more sophisticated calculations later. And there's some caveats here, right? So in order to do this really correctly, you need to take account of the fact that 0-point energy isn't the only thing that changes when you substitute one isotope for another one. There's rotation, there are excited vibrational states, there could even be excited electronic states. And you can even, and that's taking account of those, that's like the basic level of theory. Eliza and Meyer, 1947, Urey, 1947. Those papers and the papers that build on them sort of take that level of calculation. You can do even a bit better by accounting for the fact that vibrations aren't really harmonic oscillations. There's anharmonicity in them because the potential is not perfectly parabolic for real molecules and for real solids. And this has been done for a number of small molecules by various people. There's a nice review by Richer in 1977, and it was sort of rejuvenated by a nice paper by Liu et al. In 2010. I've tried in sort of putting this together and putting together the chapter to stay close to sort of standard notations, but I'll just put up this slide in case there are any small differences that become important later. So I'm going to be talking about fractionation factors, the separation of isotopes between different substances in terms of an alpha, which could be 1816 or 1716, and then define a mass fractionation law, a theoretical mass fractionation law between those substances in general for an equilibrium process in terms of the ratio of the natural logarithms of those fractionation factors. It turns out to be convenient because of these logarithms to use logarithmic delta notation, which we've already heard about a little bit today. And cap delta O17 also in terms of logarithmic delta notation. And here I've given it in per mil, but it actually turns out to be more useful when one's talking about equilibrium effects, often to do per meg or multiplying by a factor of 1,000,000 instead of 1,000. And for the purposes of this talk, I'm going to use a reference exponent, a reference slope of 0.528 unless otherwise indicated, because that seems to be what's most commonly used and has been proposed as kind of the standard one to use. Okay, so we're all here today because that factor, that 0.528 reference, is not true for everything, right? There are different materials and different processes that will give you different relationships between delta O17 and delta O18. And we're all interested in how you can extract useful information for geochemistry out of those variations. And so for simple sort of one-step kinds of reactions, and again, these are all relative to atomic oxygen. When you're talking about more complicated materials, you can get more complicated behaviors, but relative to atomic oxygen, any material will typically show a range and slope depending on what the fractionating process is that ranges from about 0.5 to 0.53, so about 3 in the second decimal place. And I've blown this up a little bit using the cap delta O17, in this case in per mil, for different types of processes. And the ones that are shown in red here, high temperature or low temperature with a light bond partner at a slope of 0.5305. And then the sort of other limit would be if you have a low temperature equilibrium involving a very heavy bond partner and a strong bond. That's turns out to give you about 0.524. And these variations have been known for a long time, going back more than 50 years, particularly in the case of sulfur. And as has been pointed out in a previous presentation, Matsuhisa did some calculations along these lines in the 1970s. Ed Young wrote a paper in 2002, and then Cao and Liu, of course, in 2011 made a really important contribution by showing that these variations may actually be useful for geochemistry in a way that hadn't quite been appreciated before. I do want to make one point, even though this is a triple oxygen isotope short course, that these kinds of phenomena are not unique to oxygen. There are some reasons why oxygen is probably the best system, the one that's going to give you the most dramatic and easily measurable variations in mass law. But in fact, in Ed Young's 2002 paper, he was proposing to use variations for magnesium isotope fractionation as a way to potentially distinguish between kinetic and equilibrium isotope effects. And in fact, wherever you look, any element that has at least 3 stable isotopes, you'll see variations depending on the type of reaction that you're talking about. They get a little bit smaller towards the bottom of the periodic table, but actually the sort of decay with increasing atomic number is not as big as you might have expected based on how other sort of normal stable isotope measurements behave. So I should point out here that a particular motivation for the work I'm talking about, even though hopefully it will find other uses, was this issue of trying to understand, to what extent when we see very small deviations from an expected mass dependence in fractionation, which we can now measure, of course, with very high precision, thanks to all these wonderful analytical advances and hard work. How big does one of these deviations have to be before you look to truly mass independent effects, as opposed to just some variation in a prosaic equilibrium type phenomenon? And so this is an important issue, for instance, in understanding the relationship between the Earth and the Moon, where there does seem to be some very small deviation in some kinds of samples, depending on what their chemistry is, what perhaps their locality is, or their petrological history. Can we explain these differences in terms of just normal mass-dependent equilibrium with a slightly varying mass law, or do we really have to call on sort of more exotic or perhaps more exciting kinds of explanations? So that was one of the motivations, and that's one of the reasons why there's a mix of high and low temperature stuff that's sort of rolled into this overall survey. Okay, so from that sort of thumbnail introduction I gave you, hopefully it's pretty clear that if you actually want to estimate fractionation factors and the mass dependence of that fractionation from a theoretical point of view, what you really need are vibrational frequencies, and to know how those vibrational frequencies shift when you substitute different oxygen isotopes into a molecule or into a crystal. And in general, we don't know that information just by looking it up in the literature. We can look up very good spectroscopic information for lots of molecules, but in general, especially for crystals, but also for liquids, that information is just not available. And so you have to find some way to model it so that you can just make a calculation. And it turns out that a really tempting method to use is an electronic structure method, basically some kind of way of solving the Schrodinger equation or some equivalent to figure out sort of what is the electronic structure of the molecule, and then you can distort the molecule and figure out how it will vibrate at equilibrium from first principles or with some amount of empirical information rolled into that model. There are always trade-offs because we're dealing with the Schrodinger equation commonly, that you can't solve it accurately for interesting systems. So you always have to make some assumptions, and the more assumptions you make, if you make them smartly, you can make your calculation faster, but it may become less accurate. It's of course nice to be able to roll in anharmonic effects, but that turns out to be very difficult, especially for crystals. You can do it for molecules, and in fact, in Cao and Liu, they explored some of this, and it's been looked at subsequently for lots of molecules. Thankfully, it turns out, however, that for normal types of anharmonicity that people usually make corrections for, doesn't seem to be a first order concern. It's probably important when one gets to sort of the per meg level of accuracy, or even perhaps 10 per meg, but it's not critical to understanding the sort of overall dynamic, overall behavior of different materials, it appears. And so in their paper in 2011, Cao and Liu actually showed very nicely that you can make pretty accurate estimations of these mass dependencies without using any kind of really exotic, high accuracy method of making your model. As long as you make a sensible choice, you seem to get a sensible answer. And I'm going to rely on that a lot because I'm going to use what I hope is a sensible choice, but nothing super accurate or exotic from the point of view of making a theoretical model of these materials. So for the purposes of what I'm going to show you, I'm going to be showing model results mostly for this chapter that are based on plain vanilla density functional theory. If that doesn't ring a bell for you, don't worry about it. with a frequency scaling, which I'll mention a little bit more detail later to explain what that is. In general, I'm not going to make an anharmonic correction for anything because most of what I'm studying are solids, and it's just really difficult to make those corrections. But it does turn out to at least be important to try to make a partial correction for especially water vapor and things that descend from water vapor, because that OH bond vibrates with a lot of anharmonicity, and so it actually does make a significant effect in that particular case. I turned out to make the same correction for CO2 and CO, but it makes quite a bit less impact in those two cases. And the results I'm going to show today, I'm going to try to put in the context of previous work. And I do absolutely want to call out that there's been a lot of previous work. Well, maybe not a lot, but there's been important previous work. Cow and Liu, as I've mentioned, in 2011, and then Hales et al. In 2018, they actually made cluster-based models of a number of crystal materials with some overlap with the stuff I'm going to talk about today. And so there's actually going to be a lot of opportunity to compare slightly different methods and see if indeed we get similar answers, which would give us some confidence maybe. Okay, so the models, we can show that they're probably doing an okay job in general just by saying, okay, they match the vibrational frequencies okay. So on the left, this is data for one crystal, diopside clinopyroxene. On the right is just all the data that was able to be correlated for the whole study. What we see is in general, there's a very good match between calculated vibrational frequencies for arbitrary phases and what's measured in the literature with Raman spectroscopy or infrared spectroscopy, or in some cases more exotic spectroscopies based on neutrons or X-rays. But there is, for the particular method we've chosen here, a slight offset in frequency of a few percent. And so we made an overall correction of 4% on the vibrational frequencies. That turns out to have very little effect on the calculated mass dependence, but it does have an important effect on the 018, 016 fractionation factors between different materials. And those are things you need to know both of those to estimate a cap delta 017. And so we went ahead and made just a blanket correction. I should also say we did a number of tests to see if this was indeed a reasonable thing, whether model parameters of other sorts affected the results. And the general conclusion was not really. They make differences in detail, but not differences in overall sense of things. Okay, so as I said, it's important to know that we're getting reasonable 018, 016 fractionation factors, first of all, because that's important for determining cap delta 017 for an equilibrium relationship, but also because that depends on vibrational frequencies and the isotope effects on those vibrational frequencies. And so it's the same thing that controls the mass dependence. And so if we're doing a good job on one, hopefully we're doing a good job on the other. And so I'm showing here just 3 examples of a comparison between the present models, various empirical calibrations, and previous theoretical methods of calculating fractionation factors where they're available in the literature. And I'm going to call this the sort of the good, the very good, and the not so good. So quartz zircon is probably pretty typical, where there's a very good general match between theory and what people have observed experimentally, if not perfect. And the theoretical results I'm reporting today are very much in line with what people have published previously. Calcite does a very good job of matching up with what's been reported previously. There's a bit of a kink around the supercritical temperature of water. This has to do with the model of liquid water that's being used, because I'm making a correction to go from water vapor to liquid water. Depending on which water model you choose, you get slightly different results. So the high temperature part, I'm not so worried about the lack of agreement. And then ice versus water vapor, that's maybe kind of a worst case scenario here, where the theory in general does not do a super good job of matching experiments. It's in the right direction. It's pretty close to the right magnitude. It's off by about 20% or so, but it's not so good. And this is actually a well-known shortcoming of the sort of standard vanilla density functional theory method that's being used here, that it doesn't do a very good job with water hydrogen bonding networks, generally speaking. Okay, so there's also now, because of some data that's been published recently, a chance to validate predictions from these models and previously published models with actual measurements of equilibrium fractionation between, for instance, calcite and liquid water. There's also good data from a paper from Zach Sharp's group of silica versus water, and other things are coming out almost every month, it seems like. And I'm just going to show one as an example to show, again, that there's pretty good agreement, it appears, between the theoretical calculations, the present models. The theoretical models are the gray lines there. And Wasbrook et al. Is an empirical calibration. You can see that does a pretty good job of matching up. It's not perfect, but it's pretty good. I also want to mention quickly this Cao and Liu, the dotted orange line, which seems to be much more deviant. That's kind of not fair of me to show. I've just put it there because I've seen it cited a little bit in the literature. In their paper, Cao and Liu made a bunch of models of carbonate, and they actually made a model of just a gas phase carbonate anion. That model does really well. It actually matches up quite nicely with the models in the gray here and pretty well with the experimental data. The model here that's more discrepant is one where they attempted to make a correction of that gas phase model to sort of what it would be like in a crystal structure. And it's the correction that's actually driving most of the disagreement there. The underlying gas phase model of carbonate works really well, as it turns out. Okay, so just a quick overview of some of the things we see. So here I'm showing a bunch of silicate species, mostly minerals, but a couple of molecules in there. And the axes here are cap delta O17 in per meg units. So divide by 1,000 if you're interested in per mil. So we're talking about sort of scale of order 1/10 of a per mil versus the fractionation factor between that species and water vapor. And this is all relative to water vapor, all with a reference slope of 0.528. And you can see that there's, first of all, an overall very similar sort of trajectory for all of these species. And this is going to be common for most of the things that are looked at, where with decreasing temperature, the cap delta O17 relative to water vapor goes down and the fractionation factor increases. And also, most silicates kind of overlie each other in the sense that they sort of overlap their trajectories, even if they're not at the same place at the same temperature. They sort of pass through the same parts of cap delta O17 alpha space as the temperature increases. And finally, there's clearly a systematic relationship here between crystal type and the cap delta O17, with the most polymerized species like alpha quartz and the alkaline feldspars having the lowest cap delta O17 at a given temperature, and the less polymerized species, pyroxenes, amphiboles, and orthosilicates being progressively less depleted in O17 at a given temperature. And you see the same basic pattern for molecules. Bridging oxygen in a disilicic acid molecule is at the lowest cap delta O17, whereas the orthosilicate silicic acid is at a higher cap delta O17. The other thing I should point out is, I'm not going to show this data, but for orthosilicates, they actually fall very similar to orthosulfates, to orthophosphates. It seems like actually even the internal atom doesn't matter that much, as long as you have a tetrahedral species with something from that second row of the periodic table. Finally, I'm going to show calcite and its related carbonates, just to reiterate this point that in Cao and Liu's paper, they looked at gas phase carbonate, and it looked very similar to what we get for calcite. And in fact, to first order, it doesn't actually matter what kind of carbonate you look at. It's the same cap delta 17 basically across the entire spectrum if you're looking at the carbonate oxygen. In fact, you can look at a nitrate. Nitratine is sodium nitrate, and that's actually very similar to calcite and aragonite. So again, if you have a trigonal molecule with species from the first row of the periodic table, it doesn't seem to matter what else is going on in that crystal. You get pretty much the same answer, which is a very interesting sort of systematic behavior. Okay, so back to the question I posed at the beginning. There really does not seem to be a way to explain even sort of 10 per meg deviations from the expected mass dependence for things like lunar basalts based on this kind of equilibrium calculation. So what's shown here on the figure on the right is, in the dotted line, what's predicted from theory at sort of a reference temperature of 973 Kelvin or 700 degrees Celsius. And you can see that the slope of that line is so much shallower than what's actually observed for these samples. There's just no plausible match at all, which is in strong contrast to the very good match we saw with empirical observations for equilibrium between calcite and water, for instance. All right, so to wrap up, we see that equilibrium mass dependence for oxygen isotope fractionation varies among different kinds of common minerals, molecules, and water at equilibrium. The basic observation here is that when you have a material that has weak or easily deformed bonds, things like ionic materials or metal oxides like iron oxides, those tend to show a high slope relative to atoms, a high mass dependence exponent. And so you would expect them, when they equilibrate with something like water vapor, to have small deviations in cap delta O17 at the most. Whereas if you have a material in which oxygen is mostly participating in very strong, stiff, and ideally covalent or partially covalent bonds, think things like carbonate, carbon monoxide, silicates, those will typically show lower equilibrium slopes and tend to have cap delta O17s markedly less than 0 when in equilibrium with water vapor at relatively low temperatures especially. And it really does seem to be sort of, is there how many of these stiff covalent bonds are, what's the basic organization of those bonds? And everything else doesn't seem to matter very much for these structures. It really does seem to be a local phenomenon controlled by the strongest bonds in the crystal structure of interest. As temperature increases, cap delta O17 rapidly decreases, so that in these sort of high temperature systems, even 10 per meg variations are very difficult to explain by equilibrium processes. Whereas at low temperatures, it seems like lots of different kinds of materials should, in equilibrium with water, give you sort of 100 per meg or 10th per mil type cap delta O17 signatures relative to a reference exponent of 0.528 or even 0.530. And we have, I didn't get a chance to address this in great detail, but it seems like, for instance, the models that Hales put out in 2018, the Cow and Liu models from 2011 and the present models, they generally agree very well. So it seems like you can sort of pick any of a number of different modeling methods that are sensible, but not necessarily super high precision, super high accuracy, and get basically the same answer, which also happens to agree reasonably well with experiments. So that's all I wanted to say. Thanks to Ilya and Andreas and to all the reviewers, and of course to the reviewers in mineralogy and geochemistry. Thank you very much.
Well, thank you, Edwin, very much for your interesting talk, and also that you to try to break it down so that also geologists can take something out of your presentation. Well, Anne, are there any questions in the chat?
No, not in the chat this time.
Any questions? Oral questions, audio questions from the audience? If not, I would like to, well, what is your opinion on experiments? I mean, you compare your calculations with experiments, but do you think that you are now at the state where you say, okay, we can calculate, anything, and experiments are not needed anymore, which I think, would be a great progress.
No, is the answer. So you can see that even with the Wasbach data, which is pretty good, and with the Silicate data, which, I mean, it seems pretty convincing, there are disagreements, and they seem reasonably systematic between the different models that have been put out and the measurements. And it's just too soon to say, right, who's wrong. But in general, if a series of experiments by different labs over time gives you an answer that disagrees with the theory, it's probably the theory that's off by a little bit. And we know that there are some things that the theory is not taking account of, like anharmonicity, that could give you maybe small differences. So yeah, I certainly do not want to argue that experiments are unnecessary. I think they work best in sort of a synergy where the theory you can sometimes do ahead of time and say, oh, this might be an interesting thing to look at. And then if somebody does an experiment that sort of matches up with the theory, that's like, oh, maybe the experiment's doing okay. Maybe I should go back and see if the theory can be done a little bit more precisely and see if it matches better. So I think the best way to do it is to have a conversation where they're sort of bouncing off each other and hopefully both improving over time.
Well, my impression is always that the theory really predicts the temperature dependence and everything very well, and sometimes there's just an offset. So I think its ideal situation is that you do the theory and then just do one experiment, and then you can see, okay, if the experiment is on the theoretical curve, then the rest of the temperature range or so is, I think, then well predicted by theory.
So the one sort of example that I've been learning a lot from is for C13018 clumping, where the first theory paper and the first experimental paper were not in very good agreement with each other. They were off by something like 30 to 50% in the magnitude of the effect. And what happens is they've actually grown closer together over time because it was realized that there was an analytical artifact associated with acid digestion. And then there are these, actually corrections for O17 have turned out to be important in that system. And there have been some small refinements in the theory so that they've grown closer together over time. Okay. And so, yeah, if the first experiment matches up perfectly with the first theory, that's always nice. But that's a luxury that we usually don't enjoy.
Okay, yeah. Any more questions? Okay, if not, then well, thanks again for your nice presentation, and we move on to the